欢迎大家来到这个网硕年会的第5届网硕年会的第4个 panel。我们在这个 panel 里面会在跟来宾有这个Pinko 素基，然后 John Brown 和 Smuggler， 还有 Michael Luther， 还有 Harry Hawking 一起来跟大家探讨一下加密主义。什么是加密主义？那我觉得，因为我们昨天的 Diva 的这个 panel，Dominic Tarr 没有办法赶来，所以说今天我们会在正式的 panel 4之前，先有请 Dominic Tarr 来介绍一下他的这个议题。我不知道大家对于任何的，比如说去中心化的这些社交网络有没有什么任何的之前的一些了解，但是我们在之前的工作坊里面其实已经跟大家感受过，如果来过我们的工作坊的话，那我们在我们的这个搭建的这个 Mesh Network 里面，已经让大家试过了一个叫做 Scalabot 的这么一个去中心化的社交网络的，它是该怎么来它的运作模式，它的所有这些东西，大家都已经感受过。那我们今天邀请来的这位嘉宾叫 Dominic Tarr， 他是我们所用的那个 Scalabot 的作者。我觉得我们可以在今天的这个开始之前，稍微先介绍一下 Dominic Tarr，然后我们再进行今天真正的这次 panel。那 Dominic Tarr 呢，他其实是一个新西兰人，然后他跟很多其他的我们的之前邀请嘉宾不一样的地方。当然了，他也是一位这个工程师，也是位程序员，但是他也不能说独一无二吧，但是他住在一艘船上，他住在新西兰的一个海边的一艘船上。那据他所说，他其实只是不想交房租，他所以决定生活在这艘船上。然后他喜欢解决任何一切的问题，他是一位 JavaScript 的他写了很多 JavaScript 的 modules， 还做了很多这样的各种各样的去中心化网络的尝试。那我们今天就邀请他来介绍他的正在做的一个新的项目。那今天他的这个演讲的这个标题叫做 Let's Rewrite the Web， 让我们重写网络。他在这个演讲中将会跟我们分享一下他现在在这个他现在正在做的事情。那网络已经发展了伴随大概我们已经30-40年的时间了，它的普及性和复杂性也与日俱增。到此为止，我们已经拥有了太多关于网络的知识，不仅是这些局域网也好，还有广域网也好，有太多的知识已经累积起来。我们认为目前已经累积到足够多的，可以再去回头看过去30-40年的这么一个历史的时候。那今天我们有请 Dominic Tarr 来带领我们一起从最原始、最简单的开始，最简单的编程工具、最简单的一些原理开始，然后该如何用这些工具、用这些东西来重写这个网络。那Dominic Tarr 先生将会与我们分享这一些的故事，这一些的一些方法。那我们现在邀请 Dominic Tarr 来帮我们来做今天的分享，谢谢。
Hi, can you see that? Yeah, that looks good.
Yes, we can see you.
Yeah, so this is Rewrite the Web. He's already said my name enough times, but I will mention that I have a new, you can generally find me as Dominic Tarr, but I started a new GitHub profile because I had created too many JavaScript modules and then they made too many emails. So .com/Dominic with Y's instead of vowels. So Rewrite the Web. So this is an idea that came out of Scuttlebutt. So if you're not familiar, Scuttlebutt is a peer-to-peer log store. It's basically a database. It's peer-to-peer, a secure peer-to-peer database where it works by you replicate feeds that you follow. which maps quite similar to how social networks tend to work, and peers can share the feeds that they have to other peers, and then you can build various kinds of applications on top of that. But one thing that I'd always wanted to have in Secure Scuttlebutt that never got around to doing it was having a sandboxing system where you could build, deploy applications via Scuttlebutt. So you could create an application, put it on Scuttlebutt, other people would load it through Scuttlebutt. And yeah, we never got around to doing that. And so now thinking about that problem, I think the right way to do it is to build a whole new system for that just focuses on that, and then rebuild things like Secure Scuttlebutt and other peer-to-peer protocols on top of that. So that's why this is called not a sandbox for Secure Scuttlebutt, but rewrite the web, because we're going to go all the way to the bottom of the problem. So what do I mean by rewrite? What I mean is to start over based on everything that we've learned so far. So not just about peer-to-peer systems, but on everything we've learned from the network and operating systems and that sort of stuff. So we've now had the web for 30 years. And it didn't, now we know a lot more about what the web actually is. So I don't mean to create the same thing again and for it not to be fully backwards compatible with all the features, because there's a lot of bad stuff, and there's a lot of things that we don't actually need in the web. So the old web is just way too complicated in my opinion. So the specification for HTML, and HTML is the least interesting part of the web. It's 1,312 pages. I really have no interest in reading 230 pages. That would be a very heavy book just about how HTML works. And then you need to understand CSS as well. That's another 430 pages. Like, how many people, does anyone know anyone who's read this? Like, very few people must actually truly understand how this stuff works. Whereas on the other hand, JavaScript, which actually does a lot, it's only 71 pages. I haven't read the JavaScript spec, but I feel like I have a pretty good understanding how JavaScript works. And I think 1,000 pages of specs for something as uninteresting HTML is unacceptable. And then there's a whole bunch of other bloat in the web. So things like IndexedDB is really not a good API, but we can't fix it now. It's too much work to add new things. Web audio is apparently another really bad one. My friends who do stuff with web audio all hate it. Applications, there's lots of things in the web that are no good, but they get added but not removed. It's just not a very good way of creating something that's good. Having one big unit, everything bundled together, a monolith, as they say. Browsers are a monolith. All the vendors of browsers need to agree on new standards, and any differences between their designs is a problem. And that's just the worst possible way of trying to have good ideas. What you really need is to have lots of people be able to try different ideas at the same time, and then whichever one's best becomes popular. So how do we get here? So when the web started back in the early 90s, the web was really just a document viewer, a network connected document viewer. And then in the mid 90s, they added JavaScript. And this wasn't really for very much at the time. It was just to add some sparkles, etc. But nowadays, JavaScript is the main thing. And it's JavaScript, basically JavaScript applications is what the web is. So the web is now an application platform or a network operating system, but it's just not a very good network operating system. It was never explicitly designed. It just accidentally evolved into a network operating system. But a network operating system is what we need. So let's make a better one. Perhaps one with some unifying concepts, like a clear idea about what it actually is. the web doesn't really have any unifying concepts, in my opinions, except for URLs and links, which is a pretty good idea. A URL is essentially, it's a text representation of the state of a state that an application can be in. That's definitely a good idea, but there's a lot more to the web that's not that. A better example of an operating system that does have unifying concepts is Unix. Unix was designed in the late 60s, and it has the unifying concept that everything is a file, which is really a byte stream. It's just like a sequence of data that's raw bytes. And the reason for this is that when Unix was created, the main use for it was text processing. So the core concept was about manipulating programs that manipulated streams of text, and then these programs could be joined together. If the input one could be a file or a program, and then that could be fed through multiple stages of manipulation by various other programs, and then it would output something. That definitely made sense at the time, and now Unix is hugely successful. Unix is basically everything is Unix these days. Most computing is Unix. Linux is the most popular server operating system. Android is based on Linux. Mac OS is based on FreeBSD, which is Unix. There's now a Windows subsystem for Linux. Some people think that near future version of Windows will just be Linux with a different user interface. So it wouldn't surprise me these days. But I think a lot of things have changed, and this idea that everything is a file isn't really relevant anymore. Everything isn't a file. Computing is a very different world to what it was in 1969. So in 1969, a large organization had maybe a single computer, and then users were all connected to the same computer via terminals, and the computers were not connected together. But in 2020, individuals own multiple computers. Like you have a laptop, you'll have a cell phone, you might have other things like a fancy watch, just ordinary things inside of your house, like cameras or your Wi-Fi router. Those have all got Unix computers on them, inside of them. And these computers are all connected to each other as well. So nowadays, I think the overriding concept should be that everything is a network. Each computer has many computers inside of it, the CPU cores. And then on top of those CPU cores, they run virtual machines, which is simulated computers. And then the applications actually run on those virtual machines. And even inside the applications, often applications have embedded languages, which is like another nested computer. You can always, one of the thing that makes a computer, defines a computer logically, is a computer can simulate, as a machine that can simulate any other machine. So there's always the possibility of nesting computers. So everything computer is a network, and a computer is a network. So all of those computers that make up that network, they can be networks as well. Every computer, it's now a network of computers, and each of those computers is a network itself. But operating systems aren't based on this idea. So the web as an operating system. So a web browser is an application for browsing the web. But these days, browsing the web really means installing applications. And every time you run a web application, it's reinstalled. So on the client, each page is run in a separate tab in your browser, and the pages don't know what other pages are running. It's like they're separate computers. And on the server side, servers run inside data centers, and developers upload their server programs, which then run on separate virtual machines. But these may be on the same physical computer, and they may not. This doesn't matter. This is hidden from the point of view of the developers. The only difference really the only logical difference between the client-side browser and the server-side data center is that the client makes a pull request to get the code it will run, and on the server side, it's a push request from the developers to the server. But it's basically the same, logically, it's the same thing. So we need a better model to describe like what is really going on. And so one thing you would look to for this is the actor model. So the actor model was created in the early 70s as a model to describe distributed computing. And it's a pretty simple idea. So there are a few things. So actors is a unit of computation. It's a computer, basically. Actors have addresses. Actors can send messages to addresses, and then other actors receive them. And messages may not they are sent, and they also may not arrive. And this is a realistic limitation because this is how switched packet networks work. If too many messages come through a switched packet network, they just drop them. And messages may not be routed the same direction, subsequent messages. So the order might change, and messages might be dropped. But that doesn't matter because we can just build protocols on top of that create reliability on top of the unreliable foundation. So TCP/IP is a protocol for deciding when to resend packets to create reliability on top of unreliability. So we can do this in general. So I think the actor model itself isn't really enough to describe what we're trying to do today. So this is what I call the actor/script model. So it doesn't contradict anything inside the actor model, it just extends it. So we can talk about sending programs around. So messages can now contain scripts. Actors can create new actors from those scripts. So a script is just a code for an actor. And the important limitation is that actors can transform or alter scripts before running them. So there's a few implications of this. So actors are nested hierarchies. So a parent actor can create children inside of it. And this means that system APIs and networks and stuff like this can just be addressed like actors. And a parent actor, because they can modify the code for children actors, they can always intercept messages intended for children by modifying the parent, the child code to pass that message to the parent first. And they can always intercept messages from children by modifying the children code so that it's sent to the messages sent to the parent first. So in the actor script model, you can send actors to other actors, but you can't guarantee that they actually run what you sent. You could send them something and they might run something slightly different, but you can build protocols on top of that to ensure that you have sufficient reliability to build that, do the things that you want to do. So we can interpret the web as the actor script model. Client sends a message to the server requesting a page, a GET request. The server responds with a script, that's the web page. The client creates a new tab, that's your actor, and that's your web page. The web backend is also the actor, fits into the actor script model. Developers send a message to a data center containing the actor. The data center creates the web server, which is an actor, and then it routes client requests to that new actor. But the web is very limited compared to the actor script model. Web clients are mostly limited to just talking to the origin of the web server that sent that script. And clients cannot talk to other clients or to arbitrary servers. They can only talk back to the server. The server is a bit less limited, but we can actually describe a lot of things that you can't do in the web with the actor script model. We can interpret smart contracts as the actor script model. So when you deploy smart contract, you send a script to every actor in the network. And then to send a message to a smart contract, you broadcast it again, and then the actor is run by every single actor in the network, and then the whole network validates. So it makes the whole network behave as if it's a single actor. To be honest, I find this idea a bit disappointing because it severely limits the amount of throughput and efficiency. And we could do so much more than making one really big, slow computer. Viruses and worms and botnets can also be interpreted as the actor script model. So a virus is a malicious script that was sent to you that you mistakenly run. A worm is a self-replicating script. So once you run the worm, it scans the local system for any new addresses that it can learn, and then it sends itself to those actors. And a botnet is a worm probably that also accepts scripts from a central actor. That's the control thing. So I think this is really the proof of the usefulness of the actor script model, is that it can even describe things that we don't actually want to happen, but happen. Another interesting thing is named function networking. So this builds upon names and data networking, which is kind of like an academic version of IPFS. It's basically the same idea. So you request data by the name, usually that's the content hash. And in named function networking, you can refer to code by its hash and then request the output of not just data, but data put through a function. So you could use this to, say, compile code or perform a query on data or something. So what would a better operating system look like? So I think the choice for now is to use WebAssembly. WebAssembly is the language for scripts, and the actors can send messages to each other. The addresses for the actors are basically arbitrary byte strings, and the parent address is the prefix of child addresses. And by having file system APIs just addressed like any other actor, then it obscures it from the user space actors in the system, whether or not this file system or whatever is actually created by user space or not. It's which gives you much more flexibility in the system. So WebAssembly is basically the perfect thing for this. So it's a low-level compile target. It's cross-platform. It's a little bit lower than the Java Virtual Machine, the JVM, but it's a little bit higher than LLVM, which is it stands for low-level virtual machine, but that's you can't take the acronym, the name seriously anymore. But it it's already in every single web browser, and it's targeted by many languages. So it's already out there. Don't need to convince anyone to use WebAssembly. And it can be, it has excellent sandboxing potential. So in the ActorScript model, I talk about modifying scripts. So one way you would modify script is prevent it from accessing certain APIs. WebAssembly doesn't even know what time it is unless you give it an address, a function, give it a method to ask the time. So it's completely deterministic. And the code memory is separate from the data memory, unlike in a Unix executable. We've compiled some C program, and when it runs, there's some data memory here at the end of the process, and then at the start of the process there's actually the code, but the code can get pointers into the code memory, and then it can modify it, and you can get that's how a lot of viruses and malicious hacks and that sort of stuff works. And if you just can't do that in the model, gives you much, much improved sandboxing. So you can implement a lot of the sandboxing I'm talking about just by disallowing messages being sent to certain prefixes. So for example, file system would be a prefix, and then files within directories and files would be prefixes of that. And you could limit one application, one actor to a specific subdirectory just by saying it's not allowed to send to messages to the file system unless it has a certain prefix, or you could disallow other prefixes. Creating a new WASM actor, you would send the bytecode to a specific system actor, which could then create the child actors. And that could be permissioned as well. One idea for building more reliability systems on top of this for like an arbitrary peer-to-peer thing is you would send a script to actor A. It would create a child actor A1, and then you would send a second script to check the first actor to a second actor, actor B, who would create another actor to check your first actor, and the first actor doesn't know that this one is just testing it and not just using it. So if it behaves incorrectly, you would detect that. And sometimes you'd need to check the checker. So you would send intentionally the wrong code to A and then ask B to check it. And in this case, B should say, no, it was wrong. And by doing this and applying some statistics, you could ensure that most of the cases got caught. And then you could be confident that you have a network that's reliably running code for you. But most of the time, it would be, you'd only end up running it on 3 computers instead of all of the computers. One thing this would be useful is deterministic builds. So you want to be sure that when you compile the code, it isn't injecting malicious, it isn't changing it, isn't inserting malicious code or Trojans or anything like that. So you broadcast it to many build servers, and then they will run it, and then you check that they all have exactly the same output. You could create a proxy actor where one actor has a stable address, and then it reroutes messages to a child actor that it controls, and then it can have arbitrary code that describes how to update that child. So, for example, it subscribes to a feed of updates, and when a new message is signed saying that there's a new version of that thing, then it would download and run that thing, but it would maintain the same address. And then if you decide that you don't like those updates anymore, you could change to another feed of updates. You could do a database query by, instead of sending just a string that describes the data you want, you could just send the code to the database. And then it could run it. So you could have a database full of just arbitrary bytes, and you'd send a parser to the data, and it would scan the data, and it could make sense of it. It could do all kinds of things. And this would work great, especially when the code is relatively small, but the data is really big, and you only need a small part of it. Then you could process a lot of data, but you process it by the data rather than sending the data to the client. A big problem with permission systems is how do you decide what permissions something should have? And I think the right way to do this is, instead of saying yes or no on all the permissions that the app claims it needs, you would subscribe to a third party that was an auditor, that they looked at what the program is trying to do, and they can judge, understanding the problem domain, what are reasonable permissions for that. And it's a lot easier to audit the permissions than it is to look at the code and understand everything. But you can say that, this program should be able to see your files, but doesn't need to see the network. So it shouldn't just cancel the network. Yeah, so you would subscribe to a feed of that you trust of permissions for a particular app, instead of having to prove every single permission. And if you decided that you disagreed with that thing, and later you could change to another permissions feed, and that would basically keep.
Do you want to conclude a little bit so that people will know what you are actually talking about? But I know, but not the other audiences. Or I can do it. But.
Oh, I mean, yeah. I'm not sure what to say there.
Or I can do that. Or. Okay. I will just speak Chinese. Dominic 刚刚呢，其实大家可能线上的同学并不是计算机背景的，所以说其实并不是很清楚他到底在说什么。那其实Dominic 在一开始的时候，他对比了很多现在我们互联网上的一些基础建设，比如说 JavaScript， 比如说 HTML， 比如说 CSS， 这些东西我觉得大家如果做过网页，可能都有听说过这些，但是这些东西都太重了，而且就是已经到几百几千页的这样的 documents 了，已经变得太复杂了。他希望用一个很简单的方式重新写这个 web， 重新写这个网络。那他刚刚也对比了很多不同的现在已有的新的技术，那他这个在最后他就希望说我们这个是他现在正在做的这个项目，他希望做好新的这个算是一个基于网络的这么一个操作系统，它可以直接运行在你的这个任何一个 hardware 上，你都不需要一个实体的这么一个操作系统。然后呢，使用这样子的这么轻量级、这么方便的这么一个操作系统，可以让我们获得更快、更高效、更棒的一个网络。So Dominic, how do you think about it?
I'm sorry, didn't understand what you said.
But yeah, actually you can switch to the English channel. Yeah. Sorry, but we do have the simultaneous interpreters. But anyway, thank you very much for coming today. Do you want to answer just one question on the Zoom?
Yes, sure.
Because like someone asked, you mentioned WebGL was needed. I don't think so. Yeah, just go ahead, please.
Why is WebGL? Well, I mean, like, you need some kind of user interface if we're going to replace everything. And Canvas, so you could draw pictures on the screen, but if you want to draw like really flash 3D printers, then WebGL gives you access to GPU stuff, which means you could do games and 3D graphics and exciting things like that. And that's part of hardware, like that's the thing about that computers, that's a feature of like what computers have. So if you couldn't do that, you'd be on the back foot, and people wouldn't adopt the new system because make a game, they would have to do it a different way, and then there'd be all this infrastructure to deploy the different stuff. So we can't really not do it and still be fully modern and up to date.
Alright. I don't. Let me check the time actually. Yeah, we do have time for another question, but do you want to answer the next one, and we can prepare for the next panel at the same time, please. Did you see the question?
Which one from Fuba? It seems to be a trade-off between storage and computation, where HTML is complicated but no extra computation needed. The new WebAssembly approach will need many computations. Well, HTML is complicated and there's an implementation for it, and it's built into your browser. And so it's still doing those computations, it's just those computations aren't running in WebAssembly. They're running in C, and that means updating or changing them is now built into the browser. And it means if you wanted to use a different system for rendering that wasn't HTML, you couldn't do that. But if you have something where it's all just, you install it, if you have a new idea for a better way of doing something, then there's nothing stopping you. Whereas currently with HTML, it's like, you just have to use it.
Okay, thank you very much. Actually, we're running out of time, so maybe we can talk later.
Thanks very much for having me.
Thank you so much. 然后大家如果有任何其他的对这个问题，对Dominic的问题，可以在未来我们的群里面跟我们提出，或者说给我们发 email 都是 OK 的。然后我会把它转交给Dominic，让他来回复大家，好吗？谢谢Dominic。